So, optimizing a fluorinated benzyl Grignard formation and attack on ethyl formate by Spencer Lorenz. So, the Grignard addition reaction scheme. So, here's our starting material. We're trying to get to this. So, first, we add magnesium turnings and THF for Grignard formation. Now that we have the Grignard here, we add ethyl formate to it. So, the Grignard's obviously a strong nucleophile. This carbon on ethyl formate is a good electrophile. So, the Grignard is going to attack this and then swing up the electrons to the oxygen. Then the electrons swing back and kick out this ester, as you can see here. Now we use our second equivalent of Grignard to again attack that same electrophilic carbon. And now we're very close to our product, so we quench with HCl to get rid of any excess Grignard and also just get to this final product by adding a hydrogen to this oxygen. All this is done under room temperature conditions, and my proposal is to actually increase the temperature during the Grignard formation and addition to about 50 degrees Celsius using a sand bath. So a similar Grignard reaction with 6-bromo, 1-hexene, when run at 60 degrees, increased the yield. This was likely due to decreased dimerization and more energy being available for the reaction. So my optimized reaction was run at 50 degrees Celsius rather than a higher temperature because I wanted to prevent the reaction from being too volatile or potentially causing other unwanted things to happen. The boiling point of THF is 66 degrees, but as you can see by the condenser, that wasn't a large concern because the condenser would cause anything that boiled to go back into the round bottom flask. So here is my first trial, which was done at room temperature, kind of as a control to compare the optimized trial to. So this trial ended up with some large contaminant, and the large yield combined with these unknown peaks kind of give evidence that there's clearly a very large contamination that occurred. Despite this, though, you can still see the product peaks, and in the TLC you can see that there's no starting material left and it's all product that's left. Just gives evidence that the reaction did occur, but at some point there was contamination that occurred. So this is definitely a concern, and to try and diagnose these peaks, we looked at literature values, me and DGL, and discovered that the most likely option would be DMSO because of this exchangeable proton here. From this one, just a large peak, and this peak as well. They're just characteristic of DMSO and H2O. So yeah, this was the H2O peak, and it's in DMSO, which is kind of seen here. I just wanted to compare it to this trial. I used this trial because it was one of my group members. They had a 53% yield and medium purity. They did not have this large contamination, so I thought it would be a better option to compare my optimized trial to get an understanding of whether the optimization was successful or not, rather than using this excessively high yield with low purity. So yeah, 53% yield with medium purity. You can see the product peaks. And then this was my optimized reaction with the 50 degrees Celsius heating that I proposed. The yield was only 29% and medium purity. You can see the product peaks here as labeled. So the conclusion from this is that because the yield was so much lower, the optimization was not successful. So the conclusions that we're going to draw from this are that I'm going to take away from this, and that you should take away as well, are that heating and really changing any variable that you believe is going to improve the reaction in some specific way might successfully improve the reaction in that specific way, but it might have unknown kind of side effects or consequences to other things that are going on in the reaction. So specifically for heating, heating may have increased the potential for side reactions in Grignard decomposition, as well as potentially increase the oxidation of magnesium before Grignard formation occurred. But because most of the magnesium was dissolved, as I saw throughout the reaction, I don't believe that was what happened. I believe that there's more of the side reactions in Grignard decomposition, but it just goes to show that yes, these unintended side effects can happen in chemistry, and they should always be considered and tested. So the other thing is, just in terms of taking HNMRs, so from that failed trial, the failed first trial, which was supposed to be a control, and all the contamination that it had. So after a product precipitates, the crystals are actually a lot more pure than the oil for NMR. So even though the oil is more accessible and it doesn't have to be dissolved, it is a lot easier to, or it's a lot more beneficial to use the crystals because they're more pure for the NMR, to put those into the NMR tube and then dissolve in the solvent. That next time would prevent the contamination from occurring. And then here is the source. This is number 2 that I used for the 6-bromo-1-hexene. Yeah, the 6-bromo-1-hexene reaction that had a higher yield when run at 60 degrees versus room temperature.